Hello, everybody, and welcome to this episode of the Ampere Developer Impact. This week, I have the great pleasure of being joined by Michelle Donani from Fermyon, Ralph Scilacci from Microsoft, and Kai Walter from ZEISS. Welcome.
Thank you very much.
And today we are going to talk about the wonderful world of SpinKube and Wasm and everything related to that. So, Michelle, let's get us started with, for those who haven't heard about Wasm, or who have only maybe heard about it in the context of it's this web technology that people are using to run rich applications in the web browser. How did it escape from the web browser, and why is it relevant to cloud developers today?
Yeah, that's a really good question. Like you said, WebAssembly started in the browser world. Folks wanted to do really take web performance and web applications to the next level. And the way that they're able to do that is by providing this bytecode format that is WebAssembly and allowing people to basically take an application, compile it from any language or any language that supports WebAssembly to a universal bytecode format, and then execute it within the browser so that you don't just have to use HTML, CSS, and JavaScript. You can now build tasks that are very compute intensive, like games, or you can do complex math and things like that. You can basically build those in one language, compile them to WebAssembly, and then run them anywhere where you can run WebAssembly. And so to do these kinds of things, you need a few different properties. You need to make sure that whatever your artifact is really small by the nature of running in the browser. You need to make sure it's very fast. It has really fast cold start times. And you want to make sure it's also portable, because you don't really want to care about the underlying architecture OS of the machine that you're running on. You just want to be able to run very seamlessly. And so these properties, the cold startup time, the portability, and of course, WebAssembly executes in this sandboxed environment that's very secure, which also you need in the browser. So these properties are also important on the server side. And so my background is in containers. I worked at Microsoft previously and at a startup that ended up getting acquired by Microsoft before that, ZEISS. And we worked on Kubernetes and containers all day long. And we worked for our customers to push those technologies to its boundaries. And they're really great containers are really great for what they do today, which is, if you want a long-running service, excellent to run an HTTP server or something like that. But if you're looking for a place to run untrusted code, or start up something very quickly, or not have to care about what the underlying architecture of your machine is, WebAssembly ended up being the thing that we really looked to make that happen. So we and a bunch of other people in the space, a bunch of other companies, part of the Bytecode Alliance, have been working on a set of APIs, WASI, WebAssembly System Interface, that actually helps you run WebAssembly on the server and not just on the browser.
If I can jump in really quickly, I mean, the critical thing is that the browser was the perfect hostile environment for the evolution of something like WebAssembly. And the interesting thing about containers is that they really evolved on the server, right? Like on a single machine. And they allowed you to move code immutably around from one machine to another. And that was fantastic and tremendous advance. But to really move just a process, right, around from one machine almost anywhere, a browser was the environment for the evolution of that, like the kind of thing I might refer to as like a cloud native binary instead of a cloud native environment that a container really is. It was just perfect for it. And that's why the focus on that evolution for the people who are see it as a future of the next 10 years of distributed computing. That's why it's so exciting.
Michelle, I'm interested to ask you, Spin, right? That's the main reason why we're talking about Wasm in the cloud and Wasm in Azure is Spin and SpinKube. What is Spin?
Okay. Well, yeah, let's jump right into it. Spin is a developer tool and runtime for building serverless WebAssembly applications. It's an event-driven system, and essentially you can scaffold an app really quickly in lots of different languages, and build your app and compile it to WebAssembly, and then run it wherever you have Spin. Okay, so Spin has a CLI that you can use to scaffold applications. You can essentially say, Spin new, I want a Rust app and I want it to be an HTTP app. And you'll get something like this HTTP Rust application. And you can see here that there are a few files in this directory. One is your cargo toml file, which describes your dependencies, your Rust dependencies. The other one is a spin.toml file that'll be new for you if you're new to Spin, as that is the basically the manifest file. It describes your Spin application. And within your Spin application, you can have multiple WebAssembly components. In this one, we have one. And the actual meat, the actual code is in the source directory. But let's actually take a deep dive into the spin.toml file first and see what's hiding in there. So this first section up here, the application section, describes the application. It's just some metadata. What is the name of the app? Who are the authors? Describe it so that people aren't completely lost. And then in the bottom section, there's a component called HTTP-Rust. You can give it whatever name you want. Essentially, you're going to use that section to wire up triggers to the component names. And so in the component section, you'll see the source, which is where does your compiled WebAssembly component live? Where does your .wasm file live? And there's also, you can give permissions and capabilities to each of the components. So this component has no access to making any HTTP requests to the outside world. Its allowed outbound HTTP or outbound host section is empty. But if I wanted to make a request to google.com, I would add this to this section, and then my WebAssembly component will be able to make that request to that domain. And in the trigger section, we're seeing that this is an HTTP trigger that we're describing, and that this component should be executed anytime the hello route is accessed. So moving forward, we're going to look at the actual meat of what this application looks like. And here we see that we have a handle HTTP Rust function, and it takes a request and returns a response. And the response is just an OK200 with the body of hello Fermyon. And if you see above your function, there is a macro that actually, it's called HTTP component. And it does a bunch of magic behind the scenes to make all of this work with WebAssembly. It does all the things that you need to wire it up so that it works the way that you would expect. And
so do you have an SDK for a number of languages? Like is the one you're showing is Rust, obviously, but
yes, exactly. We have SDKs for a number of languages: Python, Rust, Go, JS, like a bunch of ones, and you can scaffold applications in all of these languages as well, so you don't have to learn things from zero. You can scaffold and then kind of take that top-down approach. So we'll just build this application with the spin build command, and this is going to compile our application to that .wasm file that you saw in the source field. And you can use the command SpinUp to actually start up Spin, and it will basically start up this runtime environment so that you can handle different types of triggers. So we are handling HTTP triggers here, and you can see that at localhost /hello, I can curl that to actually get the response from my HTTP application.
This workflow looks kind of familiar to me. It seems very similar to the Docker workflow. Would you say that like where I do Docker build, Docker run, spin build, spin up, Would you say that Spin is to Wasm what Docker is to Linux containers, in that there's a bunch of plumbing that needs to happen in the background that kind of you take care of as part of the Spin runtime?
Yeah, that's a really good analogy. I mean, Docker did us a huge favor by building this like incredible developer experience that made container technology accessible and usable. And that's exactly what we're trying to do with Spin, is that we think WebAssembly is amazing and has incredible properties and is going to lend itself to saving people money, saving people time, running code that's untrusted code in a way that's safe for multi-tenant or environments where you need to make sure that you have certain safety guarantees. So we think that's all great. Now, we want to make sure that people can actually use it and they don't have to learn everything from scratch, because there is a lot that you have to learn to actually build WebAssembly applications.
So for me, what Spin delivers as a tool is also the developer in the loop. You have scaffolding, as Michelle mentioned, and making it available to run either locally, build and run locally, or bring it up to, I don't know, Fermyon Cloud, so that the whole inner loop for the development process is covered. It gets you going faster. This is also another aspect that Spin delivers apart from only being a runtime.
Okay.
Yeah, I mean, that's actually worth elaborating on a little bit, especially because, so with a container, when the Docker approach, you do a Docker build and you do a Docker push, and you can do a Docker pull and a Docker run and so forth, all the way through Docker. But then when you end up deploying in something like Kubernetes or a different kind of container runtime, you're now not using Docker. And so there's a little bit of a kind of a one-way, there's a beautiful developer experience, but then there's, for deployment, there's kind of a, well, we're going to go off a different direction kind of thing. And so what Kai was evaluating, what other companies are trying to use Spin for, is to both get the developer experience, but also be able to take the same application and deploy it directly in Kubernetes. And that kind of ability unifies both the inner loop, right, and also the operations cycle in a way that is really brand new.
That brings us very neatly to SpinKube. And I wonder, Ralph, if you can talk us through, first, why is Microsoft investing in Wasm on Azure? And second, today, how do you run a Spin application in Kubernetes is it as a pod, as an object? What's the right terminology?
Yeah, it's a good question. So if you're into Kubernetes, right, and you've been doing containers, you think of Kubernetes containers being executed inside pods. And so when we do our investment, our work with Fermyon and with others in the ecosystem, what we want to do is build a system where somebody like Kai, for example, can come along and say, hey, I use, in our case, Azure Kubernetes service, right? But you could say in any cloud, I use this distribution or this service, and I run containers already. I would like to make that workload better. And so when you ask me about Microsoft and its interest here, the real truth is that one of the things we learned, I think, or I'll speak for myself in this case, during the creation of the container epic, if you will, the decade of containers and Kubernetes and so forth that we've just come out of, is that we really hindered ourselves quite a bit in the beginning because we talked about how great containers were and not so much about what you wanted to do. And so we had to spend a lot more time as an industry discovering that containers were amazing in terms of their features. So Kai, for example, he's suffered through containers because he, of course, runs a million of them, billion of them all over the place, right? As does everybody else. And they're fantastic for what they do. But now Kai is looking for even more features. He's not really looking for WebAssembly. I'm going to provoke Kai and let him speak to it in a minute. But from Microsoft's point of view, what we're trying to do is experience the limitations that any engineering solution, including containers, create, and see if we can create features to get us past that, but still use the same experience, the same tools, the same kind of the best inner loop that we can find from the cloud native experience. So that's why Microsoft is interested in WebAssembly, and specifically WebAssembly components, as part of the work that's going on with the Bytecode Alliance Foundation.
Right.
It's the features of WebAssembly integrated into the utility of Kubernetes and OCI registries, Docker container registries, for example, that somebody like Kai, I'm believing, is really after. And so I'm pretty sure Kai's going to say yes.
I would say yes. And Dave, earlier you touched on limitations. Yeah, of course. If you compare a Java applet to a WebAssembly component, a WebAssembly component or module doesn't have that many features. But for me, it's not a limitation, because in most of the applications we have in the cloud, what do they basically do? They get an HTTP or a like request, process it. Maybe they access some resources, again, over HTTP. And then the question is, for me, why should I carry along almost a complete operating system in a container? I don't need that on one hand. Yeah, so it's a logistical matter for me, which hurts the density on the cluster of what I can pack into a cluster. And the second thing is, if I have this boxed environment, as Michelle was referring to, my developers are pitted for success in a way that they cannot stumble over stuff they would have available if they would have the full surface with operating system and everything. Yeah. So basically, for me, that helps that I can let the developers focus on the job, yeah? And the job has to be packed in that module or in that WebAssembly component. This is the job to be done. We take care of hosting, and we do not have all this outside influences hurting that module.
Okay. Before we get into what ZEISS has been doing, Michelle, do you want to run through what exactly SpinKube is and how it works under the covers?
So SpinKube is essentially a stack of open source software components that run on your Kubernetes cluster that make it possible for you to run WebAssembly directly from a pod in your cluster, just as you would a container. And so I'll actually walk us through this with a video. Okay, this is a SpinApp custom resource in Kubernetes. It's part of the project as well. And as you can see, the name of the SpinApp is Hello Wasm on line 4. And if you go a little bit lower to line 6, you're going to see a reference to an OCI artifact that under the hood contains a WebAssembly binary. And so where you might use container images, you're actually just replacing that with something that you're already familiar with. And you can use Spin to actually package your applications with as OCI artifacts as well. So you can see it kind of running here. And then if you actually go and check out what pods and services you have, you'll see that behind the scenes, the Spin operator has picked up the SpinApp. It's created the Hello Wasm pod. It also created a deployment and a service called Hello Wasm, which then you can curl to actually access your application. And so it's kind of an overview of how this all works together.
Okay.
And notice, if I can jump in one more time, notice that her Hello Wasm application, just like a container, is modeled as a pod. In other words, from Kai's perspective, as a user of Kubernetes, it's all the same.
Okay. And one of the things that is interesting, like, may I ask where Ampere fits into the story? Because one of the things that's interesting about SpinKube and Spin in general is that it's really scalable, right? It can use a lot of compute resources, and it's cross-platform, right? Because obviously, anywhere you have the Wasm runtime, the Wasm environment available, you can run a Wasm bundle. It's compiled to platform-independent bytecode, right?
Yeah, and that's exactly the point. Yeah, you only build Wasm once. You do not need those multi-platform builds. Yeah, you build it once, and basically this Wasm module can jump around on different types of nodes. Yeah, like
Kai, I've never asked you this, but when you were running your regular workloads before you evaluated WebAssembly, did you find that it was hard for you to focus on doing multi-arch builds in order to take advantage of ARM chips like Ampere's chips? Like, was that a resistance point for you? You're a busy person with a busy company.
Yeah, it was an effort, but it was not a challenge. You can do that, but you have to put extra energy in it. And you always have to consider it from a logistical point of view. And that also means from a deployment point of view. So whenever you deploy a feature, you always need to consider, okay, where I'm going to, what is the node pool, and what processor architecture is that. You always have another aspect to keep in your mind.
Right. The tagging of affinities, or what's the taints to say, yes, this workload can go here.
Tolerations, node selectors, yes. The whole ball of Kubernetes wax, and the CI/CD time that you don't think about because your developer is the one wasting time getting the coffee, waiting for the other builds to finish up as well.
I will say, I mean, people have been very successful with multi-architecture builds and even building natively on Ampere and creating the manifest afterwards. But it's an extra step. It's work that you need to do, and you need to figure out where you're going to run. So let me show this video screen so that Michelle can run us through how scaling works with something like Spin.
Yeah, that'd be great. So this is that same SpinApp we were looking at earlier. And all I'm going to do is update the replica count to 50. And then I'm going to apply this to my cluster. And here we're going to check out what's happening behind the scenes. So you see a bunch of pods are being created. You have behind the scenes, you can see that there are two different types of nodes that are running. I'm actually running on AKS, and I'm scaling here between Ampere's ARM64 based node and as well as a x86 node. And as you can see, and like we talked about before, really is we don't have to worry about the underlying OS or architecture by the nature of WebAssembly being a portable bytecode format, and it's just like becomes like one less thing that you have to think about. And so you can use whatever is right for your environment. You can use whatever nodes are cheaper for you. And that's a really great thing in practice and in an operating environment.
Okay. Well, that brings us very neatly. Kai, I'd like to spend most of the rest of our time together talking about what ZEISS have been doing with Spin on AKS and how you've worked with Ampere servers as part of your Kubernetes cluster to run or to evaluate this these functions as a service running on top of Spin. So this is you put together a blog post. This was actually one of the things I found when I was hearing about Fermyon and hearing about some of the work that you've done with AKS. I found this excellent blog post, which I will share. We'll obviously add the link in the show notes. But so you've been testing out some functions on Spin on AKS, correct?
That is right. Yeah, but let me rewind a bit. So let me talk about ZEISS. So ZEISS is an optics company. Yeah, and in this optics company we do many products. Yeah, so it starts with the glasses. We have microscopes. We have microscopes for surgery, to do brain surgery, eye surgery. It goes up to the semiconductor business, where we deliver the optics, the only optics on the world which can deliver, for instance, the 7 nanometer chips you today see. Yeah. So, and my job is basically to deliver the information technology to operate that business, or at least to help our business to operate that. And we are working in a kind of a core and a shell model here. That means we have our processing systems, central processing systems are in the core with a famous European software vendor. I think you can guess, yeah. And then we have the shell, and the shell is responsible basically to get in orders or any transactions with our customers prepare them, and then send them into the core. And this is exactly where we have massive workloads, where we have to process orders or messages in batches, in spikes, and so on. And this is where we heavily use Kubernetes or alike, yeah. So to host the logic, which basically receives the order and forwards it, or validates it and forwards it. Here, the challenge for us is that for certain business scenarios, we have to over-provision massively, because we would not know when the next huge batch of orders comes in. And for a huge batch of orders, we basically made a promise to the customer. Yeah, we take this 10,000 orders and we promise within, I don't know, 3 minutes for all of the 10,000 orders, we can tell you, okay, yes, we can ship. From where we ship, and we also need know where we produce and from where we ship it. Yeah. So, and this evaluation has to be done quickly, and in order to keep that promise, we have to over provision. Yeah. Basically, we always have to keep containers warm in standby, that they can carry that load immediately and process it. Yeah.
And so if we can look at the order processing system that you've been trialing on Spin, can you describe like how much traffic goes through this application?
Yeah, that depends. So what I did here is a generalization, which basically maps to what we do in real life. Yeah. So the scenario we have here is that we basically drop 10,000 orders at our gate. This is this dotted line, 10K messages scheduled at same time. So this is basically reflecting the scenario we have. We get the 10,000 orders dropped on our API endpoint at the moment, and then from that point on, the counter is running. Yeah, that means we need to pick the 10,000 orders, run it to several stages of logic. And we basically measure when all the logic is done, how long does it take for all the 10,000 orders to receive the other end, this outbox here. Yeah? This is really only a generalization. Of course, in our regular processes, you have far more components involved. But here, with that scenario, we get a very good feeling of how those components behave. Yeah? Because if you look at regular performance tests, what you often see in WebAssembly, you can hit an HTTP endpoint like mad, yeah, and you get, I don't know, 100,000 requests and whatever. You basically see the single HTTP request performance. But for our evaluation, it's also important to see, okay, how is that thing behaving in the ecosystem? Because as soon as you implement, or as soon as you introduce a new component into your system, like switching from a regular container to WebAssembly, although you only replace at certain points, the behavior of those components will change, and behavior from the context from the outside will impact the component, and the other way around. For instance, when we were doing our evaluation in Spring together with a team of Fermyon and Microsoft, we learned quite fast that SpinKube is scaling in a way tremendously fast that all the cloud resources which we basically had on the receiving end, they could not keep up. Yeah, that means you have an impact there. So if you scale like hell and your backend database or queuing system or whatever is not configured the right way, you gain nothing. Yeah, you basically mess it up. Yeah? Okay. And this is why we always test such stuff in a context, yeah, where it has to live in an ecosystem. Like you have an ecosystem outside in the wild, and you put in another animal. Yeah, you also have to see how it behaves in that ecosystem. Right. That was our approach, if that makes sense for you.
Was there a lot of work on those backend systems, like the web backends that you said that Spin was scaling so much that it was overloading systems behind it?
Here comes the kicker. We are aware that we could implement a technology like that only in coexistence with the existing technology. So we have a huge cluster to process orders. We would implement this technology, a Spin or a WebAssembly, only on, I don't know, a critical path or a path where we would gain values. Yeah? But we would not create a new environment for that. We expected, and that was the challenge for the Microsoft and Fermyon team, we expected we reuse our existing Kubernetes cluster, and at the point where we see fit, we will implement this new path of processing in parallel to the old path. You know?
Right.
And the primitives that SpinKube delivered allows for that kind of coexistence. Yeah, we can reuse the same hardware, can even reuse ARM node pools for a logic which was not allowed for ARM chips, Ampere chips before.
Yeah, that interoperability point is so important, especially for Kai's environment, kind of coming from the Fermyon side. The requirements, part of the requirements were, hey, I want to use the same autoscaler that I've been using, and I'm not going to change out some of the key components that I need, like Dapper, etc. So I'm going to run this in my cloud native environment, and we want to make sure that it works with all of the tools and plays nicely with all of the tools that I am already using. And I love that about Kai and his team. They're pushing boundaries in a very practical way, because you don't want to start from scratch. You know, you've invested a great deal in your current environment. And I think that that's how a lot of people feel, is that I want to use your new cool thing, but I'm not going to start from scratch. So show me how to make it work in the playground that I have for you. And that's the special piece about Kai's environment.
That really brings it back to the interest that Microsoft and the investment Microsoft has been making in this area as well. So, for example, I spoke a little bit about the kind of nitty gritty details of how Kubernetes and Run WASI works, the underlying shim. The real truth is that we built that system and invest in that so that Kai can not have to think about all the other things that he might have to think about if he had to have an entirely new system. Kai needed to make improvements. He didn't need to replace everything to do that. And that's where Microsoft's investments are being placed right now. We did that specifically to enable the ease of use. Kai used Dapper as a sidecar. The Dapper comes as a container. And so there was a
container sidecar on a WASM.
Absolutely, that's exactly what Kai. That's exactly.
You could do that, yeah. And so the whole industry is talking about mental load, yeah, at the moment, yeah. And also one part of my job in working with the teams is to take care that we do not overload our teams, yeah. So we do not make huge jumps or hoops in implementing stuff. Yeah, we want our teams to basically rig in the benefits, but do not need them to overtrain or train everything again. Yeah, we want to really adapt, iterate, improve slightly.
I like that.
In your blog, yeah, I do like that. Well, let's take a look at you have a video describing the process that you.
So basically here is the setup is deployed. We have the 3 services in one instance each, and we have Dapper sidecars in 10 instances. The test starts here, and the test puts now this 10,000 orders at the gate of the environment. And the first chunk of, I don't know, 5 seconds is picking 500 orders. And now you see on the lower half of the screen that the environment is scaling up to the designated 10 instances of the SpinApp. And you see that now the orders are processed much more faster, and that it is incrementally speeding up and processing the orders. Yeah. Okay. So here, I guess we will end up with a runtime of, I don't know, 34. Let's wait for it. It should come, the number 34 seconds of processing for all of the 10,000 orders. And this was the indicator for us, which we measured.
And 10 replicas was an arbitrary limit that you set just as part of doing the test. Is that correct?
That is right. Yeah. And even if you see, we already pre-scaled Dapper to 10 replicas to basically feed in the maximum load into the Spin component, because we did not want to evaluate Dapper and the capabilities of Dapper at that end. We just wanted to evaluate the performance of the component. That's why we basically passed through the load as maximum as possible on the environment.
In a leading question, Kai, you used both DS2 instances and DPDS v5, right? D2 PDS v5, which are Ampere instances on Azure, for those who are unaware. And DS is that is Intel. Is that right? Or
yeah, it's a regular x86. I would not even know. Yeah. So, but that's what we usually have. Yeah.
How did they compare?
So, if we look at the runtime heavy workload with Node.js, we could process the same number of orders in the same time with an Ampere processing or VM environment, which is 60% cheaper. Yeah. So that is also an angle. To
right.
If we have commodity workloads where performance is not the issue, but we are basically capable of saving money, we could switch to the cheaper processor, because with that WebAssembly. With a WebAssembly model, we can use use architectures or CPUs which do not have that high expectations on I don't know, memory, CPU, and processing power. Yeah, we can use cheaper resources. That's also an angle for us.
So to summarize, you got similar performance but much lower cost by using the
Wait. Not just much lower cost. What percentage of lower cost?
60%.
I thought I heard 60%. That is not a 20% discount. That is not a 35% discount. That is a massive change. And that is information that gives Kai the ability to talk to other members of his organization and say, there's stuff on the table you can reach for when you're ready. That is fantastic.
And may I ask, compared to when you were running on Azure Functions or in containers, how much of an increase in throughput did you get with running the WASM workloads?
So if I would compare it to our regular function environments, we already had a 50% improvement running with WebAssembly, coming from the bigger containers with a more massive runtime environment that, for instance, functions has. We have a 50% improvement, or only take 50% of the time. So we never were able to match those performance numbers with any configuration, classic configuration.
So to summarize, you're getting a 50% improvement in throughput and a 60% decrease in cost by using DPDS VMs instead of x86.
In the one flavor or the other.
Very, very impressive.
To focus,
That is very, very impressive. And the point is that once you do the shift to Spin, the cross-platform, you have the ability to choose whichever platform is best for you in price performance.
That is right. Yeah, we gain more flexibility. Yeah, more breathing space.
Okay.
And that's actually why we were investing. That's actually why we think Spin and SpinKube usage and AKS, for example, is an absolutely wonderful solution, because it allows the companies like ZEISS to dial in to exactly the part of engineering and operations and budget that they want to target.
So basically summarizing or repeating kind of what Ralph said, I think the two things that are really important to think about when you're talking about comparing WebAssembly to JVM or containers or any other technology is, one, this deny all by default approach. So most other technologies that you're working with, you're taking a technology that's pretty open, and you're then rewiring the security profile to turn off things, turn off capabilities that you have access to. And that's great, but sometimes that can be error prone if you miss something or you just don't realize that you have access to a certain capability. It's how a lot of exploits actually happen. And so what you get with WebAssembly, in the opposite regard, is that everything is deny all by default. You have no capabilities whatsoever. This is a sandbox environment, and you don't get access to anything unless you're explicitly given access to that thing. And so that is a really powerful part of this technology that's hopefully going to make computing and writing and building applications a lot safer and a lot easier for developers when you don't have to worry that that is even an option. And the second thing to think about when, again, comparing these technologies is that WebAssembly was born out of a beautiful collaboration. It started at Mozilla with the team there with previous technologies, but very quickly the browser companies got together. So you had Chrome, Edge, Safari, Firefox all kind of get together and more and say, okay, we want to support this thing. And within the matter of a few years, you had all major browsers supporting the WebAssembly technology. And to get there, you have to collaborate. So all of this collaboration is happening in the W3C, and WebAssembly is a W3C specification. So, and this is what Ralph was hinting at anyway. But I just want to drive home the fact that this thing was born out of collaboration and born to be run in an environment where you don't have any capabilities, and that's a really cool thing.
Yeah, it's not a bad thing. It's a good thing, and especially for those who are paying attention to software supply chain and all these kinds of things that are critically important. The environment that much of Kai's software runs in is critical to his business, but also even more critical to the business of his customers. And so that stuff actually matters. It is a foundation for the next 10 years of distributed computing.
Well, thank you very much for joining me today, Kai, Michelle, Ralph. It's been a pleasure, and I look forward to seeing you again in the future. Thank you very much.
Thank you. Bye-bye.